Oh gosh, where to start? Take a look at this blue grid here. It represents a flat surface with a slight bump at the top right of the screen near the point 2, 3. If you're used to working with flat spaces, you probably don't have to worry about using a basis too much. But when you have a grid where all the grid lines are perpendicular to each other, but the surface isn't flat, you'll have some parts of the graph that have a greater distance between grid lines somewhere on the grid. That's what we have at the upper corner here. The distance between the x-coordinates, EX, and the distance between the y-coordinates, EY, can vary depending on where you are on the surface. And I don't see any reason why we can't use the ideas of calculus to shrink down these EXs and EYs to the smallest limits they can go. Now, for those of us who are used to calculus but not linear algebra, we're used to dy and dx, but not EY and EX. A key thing to remember is path differentials like dx and dy represent the path of an object on a space, but the basis differentials, ex and ey, represent the space itself. In this picture, we see a red path where dx and dy show the horizontal and vertical displacements of the path on the space. So when the same dy happens across a longer space, it covers a longer distance as well. dy can be thought of as a fraction of ey at a particular point, and the same can be said for dx. We typically measure the path of the object only by using the coordinates of the space. It helps if you keep in mind that the grid lines in such a space only deal with location and no longer with distance. In flat space, EX and EY are the same everywhere, and so to make a straight line, all you have to do is say dy over dx equals some constant number, shown to be 1 in this picture. But with this other picture here, where the EY changes its height, we see that dy over dx being equal to the constant 1 no longer gives us a straight line. What modifications can we make to our standard dy over dx equals c equation so that we will be given a straight line, even when our basis is changing depending on our location? Well, on a past YouTube video I made, I dealt with a similar question where I decided to modify dx over ds equals c, where ds is the actual distance of the path followed. This equation is just as much of a geodesic in flat space as is dy over dx equals c. It also fails to hold true when the space is warped, so that ey or ex is changed depending on your coordinates. But I found a way to modify it so it did stay true in the video. I claimed that the straightness of the path could be retained by modifying the formula to dx over ds times ex equals c, where ex is the basis in the x direction. If I recall correctly, I did not just come up with the formula dx over ds times ex equals c out of thin air, but got it from page 72 of the book General Relativity, an Introduction for Physicists by Hobson, Efstathio, and Lazenby. I can't remember if it came directly from there or if I modified what they wrote down a bit. So if I could modify the dx to dx times ex in the formula to make it correct, why couldn't I do the same thing with dy and multiply it by ey? If I do that, I can go back to my original formula of dy over dx equals c and change it to dy times ey over dx times ex equals c. Would this formula make any sense? Well, if we modify the formula, dividing both sides by ey and multiplying by ex, we get the formula dy over dx equals c times ex over ey. Let's take a look at what this formula is saying. It seems to be saying the distance the path crosses vertically is inversely related to the distance the space increases vertically. Also, the distance the path crosses horizontally is inversely related to the distance the space increases horizontally. So when the space to cross in a certain direction expands, the fraction of the space that the path needs to cross contracts. For instance, if the space keeps increasing vertically, the basis ey is continually increasing, and the path dy will have to shrink how much it goes up vertically in terms of the fraction of ey more and more, just to keep straight. This kind of makes sense. Let's look at an example. We start with a basis with an arbitrary ey and an arbitrary ex, and the red path is simple, following dy over dx equals 1. Notice that ey and ex don't have the same distance here to emphasize their arbitrary nature. But if we follow the path to the next block over, we end up being in a space with a basis ex equal to 2 of the previous ex and ey equal to 4 of the previous ey. What would the path here be to preserve the straightness of the path? Let's use our new tool to find out. Our newly derived geodesic formula dy over dx equals c times ex over ey. Well, the constant in this case is 1, since dy over dx equals 1 for the first block. Plugging in the ey and ex for the second block, we get dy over dx equals 1 times 2 over 4 for the second block. So dy over dx equals 1/2 for the second block. That means if we use a slope where the path goes up 1/2 of the block, the path will remain straight. The visual graphic seems to indicate that. Let's do another example. In this case, we'll change the constant from 1 to 2. So for the initial block with 1 ey and 1 ex, we have dy over dx equals 2. And for the next block over, we have ex equals 2 and ey equals 5. So the dy over dx for the second block, for it to maintain a straight line according to the new formula, is equal to 2 times 2 over 5, and that equals 4/5. And in the picture, we see that 4/5 of the vertical distance in the second block is covered by dy when it comes to continuing the straight line. For the last example, let's do a fractional dy over dx for the initial block, where the slope is 1/3. And we'll make the block that comes after it smaller instead of bigger, unlike the previous examples. But the same strategy applies. The constant in this case is 1/3. The ex is 1/2 and the ey is 1/3. Plug everything into the formula. We do some algebra and ultimately end up with 1/2. And I think our picture is in agreement. Well, putting together all of these examples and arguments, I believe the formula dy times ey over dx times ex equals c might just be another version of a geodesic equation, at least for two-dimensional surfaces with perpendicular grids. I may try to find additional ways to show this as time goes on. In particular, it's useful when you already have a basis on which to draw a path on. I'm hoping to show how to compute a basis of a 2D surface embedded in a 3D space for my next video.